Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are now beginning our study of Chapter 6, Thermodynamic Models of Real Pure Compounds. This is the chapter where we are going to begin seeing the mathematical formalism that allows us to do predictions of properties for materials where we don't have a wealth of data. There are no data tables. There are no extensive graphs of the materials and the properties that we need. We're going to be looking at fundamental property relations, and we've actually done some of this before, but we're going to really hit it hard and heavy this time. First, I want to give you kind of a warning or a heads up. I am not going to write the little circumflex for per mass or underbar for per mole or whatever. Generally, these statements I'm going to make in this chapter are going to be true for both extensive and intensive, and you just simply need to be consistent in your use. So if you're using an equation that you're doing it on a per unit mass basis, then all of the variables need to be per unit mass or extensive or whatever. Okay, so number one thing. Now let's return to some of those facts that we learned way early in this course. So first of all, Gibbs phase rule. Now if you recall that Gibbs phase rule tells us that for a certain number of compounds and number of phases, how many degrees of freedom or how many variables I would need to specify in order to fully define a system. If I have a single compound, so a pure substance, in a single phase, then the degrees of freedom will be 2, which means I need 2 state variables to fully define the system properties. Well, then that begs the question, what are the state variables? These are the easy things like pressure, volume, and temperature, but then also those kind of more uncomfortable ones like internal energy, enthalpy, Gibbs free energy, Helmholtz energy, entropy. Any of those are state variables, and any 2 of those fully define my state. Now, let's go back also to the first law. If I'm looking at a closed system and have negligible changes in kinetic and potential energy, then du is dq plus dw, and I've subscripted these with reversible because at the moment that's what I'm looking at. And work reversible for a closed system is negative p dv, and reversible heat transfer is T ds. And so therefore I can convert this first law for a very specific process to du equals T ds minus p dv. And the trick here is that whereas up above it was for a specific process because Q and W are path dependent, I am now dealing with all state variables that are path independent. And this is very useful because this is our first fundamental property relation, okay? It connects my primitive properties to pressure, volume, and temperature, okay? So I now connect those to my other state variables, S, U, H, etc. So this is step 1. Now, we're going to have a lot of other fundamental property relations, or I tend to abbreviate these FR for fundamental relations. And this is our first fundamental relation, du equals TdS minus PdV. We get the others by looking at the definitions. So H is U plus PV. If I take the differential of H, I get the differential of U plus P dV plus V dP, right? The product rule. And when I substitute that into the prior equation, I find dH equals TdS plus VdP. Doing this for Helmholtz energy A which is defined as u minus ts, I get dA equals minus sdt minus pdv, and dg equals minus sdt plus vdp from its definition. So every one of these was derived based on a reversible process, but we come up with something that is independent of path. They are only dependent on the initial and final state. So this collection here is worth writing down someplace where you can find them, because these are our 4 fundamental property relationships. And once more, as a reminder, all of these are going to be valid for both extensive and intensive cases. So for instance, looking at that first one, du, it could be the extensive case, du equals TDS minus PDV, where each of those are extensive. Or it could be the per mass, du circumflect equals TDS circumflect minus PDV circumflect, okay? Or it could be the molar basis per unit mole, du underscore equals TDS underscore minus PDV underscore. So that's what I mean when I say I am not going to write these out for every possible variation. Now we need to take a brief break and do some math reviews periodically in this chapter. Math is really going to be critical for understanding this chapter. Now, for a function, x is a function of y and z, so x is a function of y and z, then I can look at how x changes by using the definition of the total derivative. Dx is how x changes with y times dy, plus how x changes with z times dz. Now, if I'm taking the partial derivative of x with respect to y, it means that if it's a function of y and z, then z was being held constant. So we put the subscript there of z being held constant for dx dy. If I have dx dz, then y is being held constant, so I put that subscript there. This makes it easy for me to identify what my variables are. So you wouldn't have seen it written this way in your math courses because the full set of variables was very obvious. Now it isn't going to be quite so obvious, and so it's going to be important that we list the other variables in our function by what is being held constant, and that is going to describe our path. The key thing is x was a function of y and z, and those show up in the 2 differentials that I have over there. And this would be true for any function of multiple variables, right? And so, this is generalizable. So now if we look at our fundamental relations, du is TDS minus PDV. What that is telling me is that u is a function of s and v. So u is a function of s and v. Similarly, dh equals TDS plus VDP. So h is a function of s and p. dA is minus sdt minus PDV. So a is a function of tv. And dg is minus sdt plus VDP, meaning that g is a function of temperature and pressure. Now, okay, what does this do for us? Well, we'll get to that in a few minutes. But I can also look at this and say, wait a minute, u is a function of s and v. I'm comfortable with v, but s? Ugh. And enthalpy also is a function of s and p. I really don't want something that's a function of entropy. I don't understand entropy well enough to be comfortable with that. It's not until I get to the 2 energy functions that I'm probably less comfortable with, A and G, where I get to variables where it's like, at least it's a function of things I understand, right? Temperature, pressure, and volume. And so these natural variables are going to be a way to clue us in on how we can use these. And it's going to be very useful. Okay? Now, what this tells me also, though, is that if U is a function of S and V, then somehow S is built into understanding internal energy. So all the thermodynamic properties can be evaluated using these simple mathematical operations. Go back to our list at the beginning. All of our variables are here. We just need to figure out how to use them. Now, another little math review is on exact differentials. So if we have the total differential for a function of x and y, then df is the derivative of f with respect to x, holding y constant, dx, plus the derivative of f with respect to y, holding x constant, dy. Or a lot of times we would say df equals mdx plus ndy, where m was the derivative of f with respect to x, and n was the derivative of f with respect to y. And when we had an exact differential, we were taught that we could test for this by looking to see if the derivative of m with respect to y was equal to the derivative of n with respect to x. Because really what we're saying here, if m is df dx, and now I look at the derivative of that with respect to y, I'm looking at the second derivative of f with respect to x first and then y. And dn dx is looking at the second derivative of f with respect to y first and then x. And for smooth continuous functions that have exact differentials, those two need to be equal to each other. And nature gives us those smooth, continuously differentiable functions. They should be exact differentials. So therefore, the second derivatives chosen in this specific way need to be equal to each other. We use this to develop Maxwell equations. So let's start with du equals TdS minus PdV. And we want to take the second order mixed partial derivatives. We want to apply this definition of being an exact differential. The fact that it's a total derivative tells us that T, temperature, is how U changes with S holding V constant. And negative P is how U changes with V holding S constant. From this, we want to take the second derivatives. So I want to take the derivative of U with respect to first S then V, and the derivative of U taking it first with V and then S. If I start with the T equals du ds at constant V, then the second derivative that I'm looking for is the derivative of V of this expression du ds. So that is dt dv, and in this step, I'm holding S constant. Similarly, the derivative with respect to S of the derivative with respect to V will be the derivative of negative P ds, and that is all. I'm taking derivative with respect to S, so for this step, it's at constant V. These second derivatives need to be equal to each other, which tells me that dt dv at constant S is negative of dp ds at constant V. Now this is a really important relationship. It may not look like it at the moment, but trust me, this is really important. This is called a Maxwell equation. A Maxwell equation simply comes from the fundamental relations and looking at the second order mixed partial derivatives. And so from U, I get this Maxwell. And you can identify it as being from U of SV by looking at those variables there in the denominator and the subscript, right? So S and V are the variables, therefore it came from the U function or the U fundamental relation. This is the full set of Maxwell relations that we get from our 4 fundamental relations on energy. Based on U, we get dt dv at constant S equals negative dp ds at constant V. And again, this one came from U. From H, we get dt dp at constant S equals dv ds at constant P. I can identify that it came from H because it's a function of S and P, and H is a function of S and P. A gives me ds dv at constant T equals dp dt at constant V. And Gibbs energy gives me negative ds dp at constant T equals dv dt at constant P. For now, we've established a lot of facts. We have the fundamental relations, which can be derived fairly easily, or you can just have them written down someplace, okay? And then from those, we can derive the Maxwell relations. You ought to be able to derive the Maxwell relations on your own. We now need to learn how to use these, and that's going to be our following videos. Thank you very much for your time.